All right, so today what we're going to be working on is vertex form of a quadratic function. Okay, we're going to look at transformations. The good news is that these transformations are going to be the ones you're going to use all the way through pre-cal. Okay, so we're going to look at how the graph moves left and right, how it moves up and down, how there's a reflection, how there's a stretch, a compression, all those things, okay? So we're gonna look at all these different things. I don't know why it's 10 raised to the 10, but we'll delete that. We'll look at all kinds of things today. We'll look at the vertex, all these different things, and hopefully find them without using a calculator. Okay, so move that out of y'all's way. Okay, so vertex form, there's your formula. Y equals, or f of x equals a, then x minus h squared plus k, where a cannot be 0. Why can a not be 0? Why can a not be 0? Yeah. Okay, I get what you're saying with that, but what happens if a is 0? What are you left with? Do it.
If a was 0, then you just have k left in the equation.
Right, we would just have k left in the equation. Well, that takes away this part right here, the square part, and it's no longer a quadratic function. Squared disappears, okay? So then we're just left with a linear function, okay? A constant. Okay, so your vertex is hk. Notice how it says where h is the opposite. So you're always going to do the opposite of what's inside here. So if it's a positive 4, the first part of your vertex is a negative 4. All right, if it's a negative 7 in there, the first part of your vertex is a positive 7. Okay, you just do the opposite. Okay, always change the sign before plugging it into the equation. If a is greater than 0, it opens up. And if a is less than 0, it opens down. Okay, so this is all the good information about the vertex form. Okay, it's called the vertex form because we can literally take out the vertex. We'll do standard form tomorrow. Standard form is the one you've been seeing, the ax squared plus bx plus c. Okay, all of that is the same. Okay, so for these 3 examples, I want you to tell me the vertex, which way it opens, and we'll talk about the axis of symmetry afterwards. So go ahead and just tell me the vertex and if it opens up or down. Okay, can someone tell me my vertex and which way it opens for the first one? Good morning. Okay.
Vertex is 2, 3.
Okay, and which way does it open? Good. Okay, so our vertex is 2, 3, and it opens up. So, think about what an axis of symmetry means and the shape of the parabola we're looking at, okay? So if a parabola looks like this, and if we're looking at symmetry, naturally we know that it is something that has to cut it down the middle, okay? So if it's cutting down the middle is where our vertex is. So what would be our axis of symmetry here? Let me go ahead and draw this out so you can get a visual. If this is the problem we're working on, this is 2, 3, clearly not drawn to scale. What value is that cutting down to? What value is that?
2.
2, okay? So if you think about it, our axis of symmetry is going to cut down through our x value of our vertex, okay? So with your axis of symmetry, and get in the habit because it's going to be counted wrong if you don't do it, it's an equation of a line. It needs to be x equals 2. Do you have a question? Okay. So it has to be x equals 2. Get in that habit of doing that. So the good thing about it is once you found the vertex, your axis of symmetry is just copy paste. Like a gimme point, okay? So now that you know what an axis of symmetry is, fill in the other 2 problems. Okay, who has the answer for part B for me? Yeah, go ahead.
Vertex -5, -6.
Okay.
Opens down.
Opens down. And what's my axis of symmetry?
X equals -5.
X equals -5. Good. Okay. Remember this negative here tells me that it opens down. Take the opposite of what's inside the parentheses. So -5, -6. Okay. And the last one. Does anyone have my answers for that? Let me send my page. Yeah, go ahead.
Vertex is 4, 2.
Okay.
It opens down.
Okay.
The axis of symmetry is x equals 4.
Equals 4. Good. Does anyone have any questions on those? Hopefully it's coming back to you a little bit from Algebra 1. It's been a while. Hopefully it's diving into some kind of memory there. Okay? All right, so let's talk about graphing these. So we've already talked about the vertex, which way it opens, and the axis of symmetry on these. Okay? So every problem you're going to start off with those exact things. Okay? So if I say, and we've already done these, but now I have the graph next to them. We have our vertex, it opens up, and my axis of symmetry is 2. Okay? So let's go ahead and graph that. All right, so if I plot the point 2, 3, the axis of symmetry goes straight down it. And it opens up. We're not just going to draw a parabola from here on out. Okay, we're going to give me at least 3 points. That's my rule. I have to have 3 points from you. So you already have the vertex, and I need 2 more. Okay, so there's a couple different ways you can approach these problems. The good news is we've already got one. If I have an eyeball over here, I'm going to have an eyeball over here. Okay, that's how the axis of symmetry works. So all I have to do is find one other dot. So what I would suggest doing is looking at your axis of symmetry, which is at 2, and just pick an x value either right or left of it. Okay? So you can pick either 1 or 3. In reality, if I can speak correctly, you can pick anything you wanted to. But if you plug in something like 10, 10 minus 2 gets you 8. 8 squared is 64. Then times 4. I don't think you want to graph that all the way up there. Okay? So that's why I look at the axis of symmetry, and I look to the left or I look to the right, and I say, I'm going to pick one of those to plug into my equation. Okay? So what I'm going to do is I'm going to take 1. That one's easier for me. And I'm going to plug it into my equation. Go ahead and figure out what that other dot is. Now, naturally, what did y'all just graph for?
Okay.
Your calculator. What kind of calculator do you have? Graphing calculator. What are we trying to do by hand? Graph. So we won't be able to use a calculator to do simple math, okay? We're trying to do this by hand. If we use a calculator, nothing's stopping me from plugging it into y equals and looking at my table, plotting my points, and calling it a day, okay? So, let's do our order of operations. 1 minus 2 gets me -1. -1 squared gets me 1 times 4 just gets me 4 plus 3, which gets me 7. Okay? So I plugged in a 1 and I got a 7. So I plot that point. So now all I have to do is hop across the axis of symmetry. And it better be going up because that's what I said it's going to do. And now I have my graph. Okay, so make sure that's in y'all's notes. So they already give you their vertex. You determine if it opens up or down, then the axis of symmetry. Plot that. And then simply just use a good old t-table, if you will, by plugging in a value and getting the y value. And that's your other point. Okay? Let's talk about domain and range for a second. Domain, we talked our x values. Range are our y values. What x values is this parabola using? Remember, it keeps going. What x values is this parabola using? Yeah. Do I?
He's like all that guys.
I just can't hear you. What?
It doesn't he's like all of them. Like
Yeah, all of them. All real numbers. Okay? So if you use the fancy R, I'm going to try and break y'all away from that. we're gonna start saying that it is from negative infinity to positive infinity. It's all of them, okay? Every single x value. Here's the kicker. That is your answer every single time for a quadratic on a domain. Every single time. How cool is that? It's like if I told y'all that number 1 is always going to be A on my test, you'd believe me then. But when I tell you something like this, you're like, I bet it's something else.
How is it negative infinity if there's a minimum?
Do what?
How is it how is it negative infinity if there's a minimum on the problem?
X values. We'll get to Y here in a second. But your X values, notice how this is used, and then it's going to keep going. All your X values. Now your Y values, we have a stopping point. And what's our stopping point here? 3. So we would say it's anything greater than 3. Okay? Anything greater than 3. So for right now, if you put Y greater than or equal to 3, I'll accept that. We're going to get to the point where you're going to write it with the infinities later. Okay? Okay, so I look at my range, my Y values. My graph doesn't begin until 3, and then it goes on past that. So that's why we said Y is greater than or equal to 3. Okay, go ahead and graph the next one and give me all that information with it. Something. Don't forget, in your first period today, you have a fire drill, so it doesn't freak you out. If for some reason we had a fire drill in this particular classroom, we would just go, or not a fire drill, probably a real fire. We'd just go out this door right here, and then we'd go out that back door. Everything else we would stay in this room. So it seems almost trivial to put that it opens up or down. You're like, why? That's so silly. Why do I have to put that? Okay. For the reason of when you start graphing and you for some reason mess up your math somewhere, that if all of a sudden you said it was supposed to open up and it faces down, then you know you did something wrong, okay? So it's an easy way to check yourself, okay? So if I look at this problem and I say my vertex is -5, -6, I know it opens down and my axis of symmetry is x equals -5. I don't need that. Okay, so if I graph down here somewhere, and my axis of symmetry comes from that, okay? This is supposed to open down. I hope it does. So if this is -5, I might plug in -4 or -6. It doesn't matter, okay? So let's say I plugged in -4. -4 plus 5 gets me 1. 1 squared is just 1. Times -3 gets me -3 minus 6. So if I plugged in a -4, I get -6. So I have the ordered pair -4 or -9 is what I meant to say. -9. Okay. So then I can plot that point. -4, -9. Which I think I need to go a little more. It's just off a little bit on calibration. Hop across my axis of symmetry. And I have my parabola. Like I said, my board's off a little bit. But I said it was going to open down, and it better open down after I've done my calculations. If not, that's a quick way to say, whoops, I did something wrong.
Oh, I just figured it out.
Okay. So what's my domain? I knew y'all wouldn't believe me. -infinity to infinity. Every single time you do a parabola, all real numbers, -infinity to +infinity. It is a gimme point, just like your axis of symmetry. Copy paste. My domain, -infinity to +infinity. My range, however, is what? Yeah.
Y is less than or equal to -6.
Y is less than or equal to -6. So the good news is that is how our vertex, the Y value of our vertex, is going to be right there, part of our answer with range. Okay. Any questions on how to graph using the vertex form by hand so far? Okay, we had one more that we did. Well, I thought we did. C, go ahead and graph C that we did. You've already done the information on it. Now graph it. right, so notice that the negative is on the outside of the parentheses, okay? So if it helps you to put a -1 there, you can. So that way you don't get that confused. If I plug in 3, so 3 minus 4 squared, so 3 minus 4 gets me a -1. But -1 squared is just a +1. Whoops, as I write a negative. But times the negative that was in the front, I get a -1. Okay? So at 3, I'm at -1. Hop across the axis of symmetry. And I have my parabola. What's my domain? Aha! Starting to believe me now. -infinity to +infinity. Okay? What is your range?
Y is less than or equal to 0.
Y is less than or equal to 0. So my Y values start at 0, and they only go down from there. Notice how none of my graph is up here. Okay? So that's why it's Y is less than or equal to 0. Now, when we get to the point when we start doing infinities and stuff like that, you've done the hard part. Okay? So what this means, if I say Y is less than or equal to 0, I'm saying that it's everything from 0 to -infinity. But we never put it like that. We always put the smallest number first. So all we would do is we would write, and I'll talk about brackets and stuff later. We would go from -infinity to 0. And it'll look like that, okay? But we're not there yet, but that's what it's gonna look like, okay? Just like up here on this one, we said that it was less than or equal to -6. I would do -infinity to -6, and so on, okay? The other ones, if we were going up, it'd go from that number to infinity.
I saw something last night. Isn't it a parenthesis on the left because it's infinite and a bracket on the right because it's finite?
Yeah, so basically that's exactly it. So we don't know what infinity is. It goes on forever. So it has a parentheses on it because we don't know, okay? It's infinite, it keeps on going on forever. But because this says Y is less than or equal to 0, it actually equals that amount, then yes, that gets a bracket. Good job. But just, these are things that I want you to be exposed to, because again, I haven't seen that state test. I don't know what it looks like. They could show up with that, or they could show up with this, or they could accept both. I don't know, okay? Any questions on those? Okay. Let's talk about transformations, okay? This looks like a lot on one side, but it is a really good piece of information and a one-stop shop is what I like to call them. Okay, I used to have this divided out. Each little thing had its own slide. But knowing that, hey, when I look at an equation, if I look in front of the parentheses, I know I'm going to find the reflection and vertical stretch and compression stuff. Bless you. I know that when I look inside the parentheses, that's where I'm going to find my left and right. I know that when I look at the value on the other side of the parentheses, that's going to be my up or down. So this is a one-stop shop. So notice how the reflection is only talking about the negative. And then A itself, we're going to look at vertical stretch and compression. H is still the opposite. You see a plus sign in there? It makes you think, oh, I should go right. Because rights are to the, or positives are to the right, okay? But it's the opposite. And then outside, which that has moved. There you go. Your K value If it's positive, it goes up. If it's negative, it goes down. So I always say this trick of good dog, bad dog. Did any of your Algebra 1 teachers use that reference? Good dog, bad dog? Okay, how many of y'all have a really good dog that does what it's supposed to, minds you, all of that? You have one? Okay. How many of y'all have a bad dog that no matter what you tell it to do, it does the complete opposite? Okay? So if you think about it, that's what's happening here, okay? When you have a bad dog, that dog's got to stay in the fence, okay? You don't trust it to do what it's supposed to. It does the opposite of what you tell it to do. So that's why I say inside here with this H is a bad dog. It does the opposite of what it's supposed to do. But a good dog, K, out here, it does what it's supposed to. You trust it. You say, hey, I know when you are outside, you're going to do what you're supposed to, okay? So that means you go up when you're positive and down when you're negative. Yeah.
Can I say what my algebra teacher used to tell us?
Yeah.
It used to be that the parentheses were a house. You change inside the house, but you don't change outside of your house.
Oh, that's neat. I've never heard that before. You change inside the house and you don't change while you're outside the house. I hope you don't, but unless you're in an area. Yeah.
What does left H, right H?
That value. So if it's positive here, you would go left that amount. And if it's negative, you'd go right that amount. So if this was 4, we're going to move the graph to the left 4 units. Okay? So the good news is I can easily take this 2 away. Or not. I could take away this 2. And it could be to the 3rd power. Same transformations. I could take away these parentheses and turn this into a square root. Same transformations. I can take this and turn it into an absolute value. Same transformations. That's why I do this the way I do it. Because when you go to pre-cal, you're going to go through all those different functions, and knowing just this one line is going to help you with any function they can throw your way, okay? Including trig functions, right? You're going to look in the same location for the same transformation, no matter what kind of function it is, okay? So your fence here is going to be the same, no matter what, okay? Kind of cool how that works out. There we go. All right. So this is why I do that one liner. So then that way, I look at the function and I say, there is a number in front of x squared. That's my a value. Is 3 greater than 1 or less than 1? Greater. So it's a what?
Vertical stretch.
Vertical stretch. What is that doing? That is making the graph stretch vertically. Okay, it's pulling it up. It's making it narrower. Okay, so if you think about it, on the graph, if this is normally x squared. That's a bad representation because it's not gonna look like a stretch. So if this is normally x squared, we would take every single y value and multiply it by 3. And look what would happen. This, of course, still stays at 0, but if this is at 1, this is now up at 3. So it's stretching it vertically, and it becomes more narrow, okay? A vertical compression is meaning it's making it wider, okay? It's compressing it down, all right? So that's the difference between those two. And then when you get to pre-cal, you're going to see the horizontal stretching compressions, okay? We might do a little bit in Algebra 2 just to get you ready for pre-cal, but for the most part, that's where you'll see those. All right, so go ahead, and that's the only transformation that happened here. Do not force other transformations to happen because you're used to seeing a bunch, okay? Go ahead and tell me all the transformations happening in those 3. Okay, looking at this top right corner, someone tell me all the transformations that are happening there. All right?
It's a vertical compression.
Okay, so be careful. Look at the difference between what each thing is pointing to. So only the number value is your vertical stretch or compression. The negative that's in front reflects over the x-axis. And so we'll get to a point too where we'll include reflecting the y-axis, but not with quadratics, okay? So reflects the x-axis, okay? And what was the other one?
Right 3.
Right 3. Okay. What about this one down here? Who's got that one? Yeah.
Vertical compression.
Vertical compression. What else?
Moving up by 3.
Up 3. Okay. So that 3 is outside of the parentheses. It's moving up 3. Okay. Good job. All right. What about the last one over here? Okay.
Vertical compression.
Vertical compression. Okay.
It's gonna go left 2,
Left 2. And what else?
up 4.
Up 4. So yes, that last slide, very intimidating. A lot of words. It's all in your face. But now I can simply just start left to right and follow all these equations down and pick out the transformations that are happening. Okay? Anything that is not an x, parentheses, and the square is a transformation. Okay? So anything that's not an x squared or in the parentheses or whatnot is a transformation. Okay, so what does some of those things look like? Okay, let's look for something simple. Let's look at this one here. Y'all all have parents, whether you like them or not. You all have parents, okay? You came from somebody, all right? So these graphs come from something as well. So I just said, if it is an x squared, anything other than an x and a squared, it's a transformation, okay? So x squared is the parent function, okay? Anything extra is a transformation. So if I want to graph by using transformations, I would say, okay, well, the parent function is x squared. Well, x squared, if I do 0, 0 squared is 0. 1 squared is 1. 2 squared is 4. And I could keep going if I wanted to, okay? But that's the parent function. That's home for it. That's where it begins. But on this problem up here, y'all told me that it reflects the x-axis and it moves right 3. Okay? So I'm going to start with every dot. Can't really reflect here, but I can move it to the right 3. Okay? Same thing here. I can reflect this dot here, down here, and move it right 3. I can take this dot, reflect it, right 3. Same thing here, reflect this one, right 3. And notice, I have the same graph as I did graphing by using the vertex and plugging in another point. Okay? Now here's the thing. Just like in anything I have y'all do, if you understand this way, graph it this way. If you understand what we did before, graph it that way. But you still have to know how to find the transformations. Okay? I don't care how the graph appears. Just without a calculator. Okay? But as long as you can tell me the transformations, if the other way we were graphing things made more sense to you, by all means, do it that way. Okay? Any questions on those? Okay? So, vertex form to standard form. Woo, this is why we love algebra. Okay? This is what we live for with algebra. Those things where we just like get after it and we do it and it makes sense. We don't have to think about it. Maybe a little bit of thinking, not a whole lot of thinking. Okay? If you want to put me in a padded room with a jacket on, then square everything inside those parentheses. Because that is exactly where I'll go. Okay? Do not square everything inside those parentheses. X minus 2 squared is x minus 2 twice. Do not just say, oh, it's x squared minus 4. Got it. Doesn't work that way. Please don't do that.
So it's the quantity x minus 2 squared?
That's exactly how it's phrased. Okay. So you would write x minus 2 twice. Okay? Go ahead and simplify that down. Whether your Algebra 1 teacher called it double distribute or FOIL or anything of that nature, do that. Do you have a question? I thought you had your hand like kind of raised like that. Whether your teacher called it double distribute, FOIL, anything like that, go ahead and simplify that. Like I said, the good old algebra stuff. All right, so if I multiply my x's together, negative 2x minus 2x plus 4, and then I have my plus 3. Combine like terms, I should end up with f of x or y, it doesn't matter, x squared minus 4x plus 7. So we went from vertex form to standard form. And standard form is what y'all are going to be working on tomorrow, okay? All right? Try that one. So you can approach this one a couple different ways. You can wait to incorporate the negative 2 after you FOIL or double distribute. You cannot, however, distribute that negative 2 in before. Okay, you can't say negative 2x minus 2 and then square that. It doesn't work that way. Okay? So if I start off here, one method would be if you wanted to distribute the negative 2 to one of the x plus 1s, that's fine. And then double distribute. Okay? Me personally, I like to leave it at the end. So if I say, and I hope y'all will start getting into the habit of realizing what you're doing, that you are adding these two together and you're multiplying them, just like it is for factoring, going opposite. But I could say x squared, then I have 1x plus 1x, so that gets me 2x, and then 1 times 1 gets me 1. If you're not there yet, don't worry about it. Keep doing what you're doing, okay? And then plus 3. Now, I can distribute that negative 2 all the way through and then go from there. So let me move this away. Okay, there we go. So negative 2x squared plus 4, whoops, negative 4 minus 2 plus 3. And my last step would be negative 2x squared minus 4x plus 1. Okay? So no matter if you distribute the negative 2 to one of the x plus 1s and then double distributed, or you waited and after you were done double distributing, okay? Any questions on those? Let's see what I have behind slide number. These are just more examples. Okay, let's do one more of these and then we'll call it. So let's do this one down here. So again, if you're not at that point where you realize all you have to do is add the two numbers here to get your middle term, multiply them to get the last term, that's exactly what you're doing when we're factoring. We say what two numbers multiplies to get 16, but add to get 8. That's how we get those. You can write it out, do your 4x plus 4x, and then plus 16, and then combine like terms after that. Okay. Any questions on going from vertex form to standard form? Okay. Any questions in general from the lesson today? Hopefully it's a reminder, a refresher. Yeah.
Like f of x equals equation of right?
Yeah. Y and f of x are interchangeable. This is function notation. That basically just says I can plug in something for x, but says that. So either way. All right. So